So, the integral test for series. So if we have f is positive, continuous, and decreasing. So basically what you have to keep track of here is there's three conditions that have to be met. F has to be positive, f has to be continuous, and f has to be decreasing. Now this says for x greater than 1. What you would want to establish is that that works for whatever the series starts at. So if it starts at n equals 1, then all of this needs to be true for x greater than 1. If it starts at n equals 2, then for x greater than 2 is what we're looking at. So basically where your series starts is going to dictate where this has to start happening. So if f is positive, continuous, and decreasing, then our sequence can be written as a function of n, then the series for the sequence a sub n and the integral from 1 to infinity of f of x either both converge or they both diverge. So basically, in a problem like this, when we're given the series, we would start by equating our sequence to a function. And what we would do is we would evaluate whether the function is positive on its domain, continuous on its domain, and decreasing on its domain. Once those three things are met, then we can apply the integral test, which says, rather than looking at it as the sum of all the individual values within the sequence, we're going to integrate f of x from 1 to infinity. And if this integral, which takes into account all real numbers, so this is kind of another one of those where we jump into the reals. If it works there, it should we're working the whole numbers, right? So it's that kind of same idea there. So if we converge here, then our series has to converge as well. Or if we evaluate the integral and it diverges there, then it's going to have to diverge as a series as well. So whatever the integral does, so does the series. Okay? Now, with this test, something to note. When we evaluate the integral, when it converges, we're going to get an actual value. However, that value for the integral is not necessarily the sum for the series. So when we say that our series will converge, it's not one that we can say what it converges to. It just knows that it does converge to something. And then if it diverges, we don't even have to worry about it because we know it's not going to go to a certain value. So with our geometric series, when we determined that it was convergent, we could actually calculate the sum of that convergence. With an integral test, there's no way to tell what it converges to, only that it does converge based on this test. Does that make sense? Okay. So an example, if we have the series from n equals 1 to infinity for e to the negative n. So when we look at this one, the first thing we would do is essentially convert it to a function. So f of x would equal negative, or e to the negative x. Now at this point, before we even start the integral test, we need to check our three conditions, because if those aren't met, then there's no point in doing the integral test because it only works under those specific conditions. So condition number 1 was that it is positive. And on a lot of these, as far as showing your work for this, I want you to list so that I know that you actually took into account the three conditions. So number 1 is that it has to be positive. And for this, all you have to really do is just take a look at the function and decide. So e to the negative x, will that always be positive? Yeah, so if I go 1 over e to the x, it can't ever be a negative value. It's always going to be positive. So then you put like a little check mark. I know that this is the case. For number 2, we had to show that it was continuous. I would. I mean, it doesn't necessarily matter per se, because if at any point if you find one doesn't work, then it doesn't matter what the others do, so you can do it in whatever order, as long as the three are checked. So for the continuous, you'd have to think about, well, are there any asymptotes? Would there be any discontinuities anywhere on our domain? And so, yeah, from n equals 1 to infinity, we should be continuous the entire way. So again, you can kind of just check it off. We checked it, we know it's good. Now for the third one, which was decreasing, this one I do want to see a little bit of work for. So if we want to know if a sequence is decreasing, what were our possibilities? So there's the difference test. We could subtract, so find e, or a sub n plus 1 minus a sub n. Let's see how the difference looks. We could do the derivative test, so find the derivative and see if it's negative on its entire domain or vice versa, or positive. And then there was also the ratio test, right? So if we think about this one, with it being e to the x, the ratio and difference tests might be a little tricky, so or if we think of e to the x, that's a very easy derivative to work with. So if we do f prime of x, we would get negative e to the negative x. And if I think of this on the interval from 1 to infinity, that will always be negative. So no matter what we plug in for x, because of the negative out front, we're always going to be less than 0. And so then because of the derivative test, we know it's a decreasing sequence. Okay? So the first two should be pretty quick. The third one requires just a little bit of work. So derivative, ratio, difference test, however you want to do that, to show that it's always decreasing is up to you. Okay? Now from here then, we can use our integral test, which means we want to evaluate the integral from from 1 to infinity. And we're going to integrate.
Will it ever not be 1 to infinity?
Yeah, if the series starts at like n equals 2, you go from 2 to infinity. So you always, and as far as the domain, for like the decreasing and things like that, or the positive and stuff, you always go off of the starting point of the series. So wherever it starts, your integral starts. So if we integrate if we integrate from 1 to infinity e to the negative x dx, what problem do we have right off the bat? An infinite bound. So the first thing we need to do is rewrite as a limit. So the limit as b approaches infinity for the integral 1 to b of e to the negative x dx. And then from there we are going to do our integration. So if we integrate e to the negative x, we would get negative e to the negative x. And then we're evaluating from 1 to b. So when we plug b in, we get negative e to the negative b minus negative e to the negative 1. Okay? And so, if we take b to infinity, what's going to happen here? All right. So we got to look here, since this is e to the negative b, this is equivalent to 1 over e to the b, right? So if I make b go to infinity, that means I'm going 1 over a very large number. So this is actually going to go to 0, which leaves us with e to the negative 1, or 1 over e. So, since our integral, our indefinite integral has an actual value, what does that mean about my series, e to the negative n? It converges. So once you've shown this, now you say this converges by the integral test. Every time you're asked about convergence or divergence, as soon as you've shown, so whatever test you've chosen to investigate that particular series, you need to make sure you draw your conclusion and give what test you used to prove that. So every one of these problems has to be converges by this test or diverges by this test. Okay? Any questions on that one? Okay.
So would this be the second test you use after the first?
It really just depends on what's inside, what sequence is inside your series. And that's one of the things that will kind of, as you continue to see more and more tests and you start to see more and more problems, you'll start to see patterns. Like you're going to see, okay, this is my sequence, well, this looks like this, so I'm going to try that test and so on. But yeah, as far as like the nth term is almost always like the number one go-to. If you get a limit other than 0, you know it diverges. If you get 0, then you got to go to something else to see what happens. But this is always a good one. I mean, if it's something that's easy to integrate and it has the 3 conditions met, then yeah, this would be a pretty easy one to work through. Okay. Oops. Go ahead and take a look at the next one here. Okay. So if we take a look at this one, so if we take a look here, first step's going to be convert to function notation. So f of x is going to equal natural log of x over x. Now, as far as our conditions go, so the positive, if I have natural log of x over x on my domain, so if we notice we're going from 2 to infinity, are we going to be positive? Yeah, so natural log of x is always going to increase, x is always going to increase, so the positive is good. How about continuous? Yeah. As far as the only concerning point would be, yeah, x equals 0, and since that's not part of our domain, we don't really have to worry about it. So what we're concerned with, we're going to be continuous. And now as far as decreasing, we would check, yeah, we could check with the derivative. So if I find the derivative, so f prime, so if I have natural log of x over x, my derivative would be okay. So using our quotient rule, we take the bottom times the derivative of the top, x times 1 over x gives us 1, minus the top times the derivative of the bottom, so natural log of x times 1 over the bottom squared. Now, on this one brings up an interesting case. So if we start to look at this one here, and we think about this idea of decreasing, so decreasing means that our derivative has to be, it has to be negative, right? If the derivative is negative, then we know that our original function is decreasing on that domain. Now, if we think about this, and if you use your calculators, if you take 1 minus the natural log of 2, so someone do that for me real quick. I want
It's a negative number. It's 0.3.
all right, it's actually a positive number, right? So 1 minus natural log of 2, which is our starting point, would be a positive over a positive, which means our derivative is actually positive at that point. Now, as we continue on, though, what's going to end up happening? It is going to become negative and maintain its negative course throughout. So, one of the things that you might have to kind of work with or think about on these types of problems is the initial part of our function. Okay. So when we test this whole decreasing portion, it might actually increase for a little bit to begin with. What we're really trying to determine is, at some point, does it become monotonic and never go back? So does it always decrease in this case? So while it doesn't start off that way, because we're going to continue increasing the values of x, that means the natural log of x is going to continue to increase, which means we're going to start getting negative numbers and never go back. Does that make sense?
Why is it like that? I mean, how many numbers should we test before it turns negative?
Generally, if it's something like this, it's going to be something that's pretty quick to change. Or it's going to be something that's it's very obvious that you're taking a constant minus something that's increasing on the interval, which means at some point it's going to surpass the 1 and it's never going to go back down below. So it'll either be something that's very obvious that it's eventually going to be decreasing on the entire thing, or something that you'd be able to test and get to pretty quickly.
So since it has to be decreasing for the integral test to work, why is it able to not be decreasing? Because most from...
So yeah, when we're looking at the decreasing, the biggest issue is because the whole idea is as we go to infinity, right?
Mm-hmm.
So even though we're going to increase slightly for a while, we are on almost the entire domain going to be decreasing. So we're just trying to figure out, is there a point where we become monotonic decreasing? Does that make sense?
Yeah.
And if it does, then we're still okay to use that integral test. But if it's one that kind of goes back and forth, or if it's one that stays positive or whatever, then that would be something we can't use. But even if it starts doing something initially, but then eventually as you approach infinity is decreasing continuously, then you're fine. Okay? So then, at this point, we would integrate, in this case from 2 to infinity. Okay. Since we have an infinite bound, we make it a limit. And if you want to, on a problem like this, you could go straight to the limit portion if you want to, skip the whole set up the integral, then change it. So that's always an option for something like this, since we're going to see it a lot. So now at this point, if we want to integrate, what do we have to do?
U and B. U and I, or no, D and I call
So you want to integrate by parts?
it.
We can. We could integrate by parts, but U substitution would be a much easier version because we can let U equal ln x. Okay? So U is going to be natural log of x, which means du is going to be 1 over x dx. So really what we have here is the limit as b approaches infinity of the integral from 2 to b. This all becomes u du. So then when we integrate, we You guys okay if I skip straight to replacing natural log of x with u again? Okay. And we're going from 2 to b. You could leave it in terms of u, but when you do that, what would you have to remember to do? Change the bounds that you're working with. So you'd be going from the natural log of 2 to the natural log of b for u squared, and then you'd have to evaluate from there. So it gives you the same answer either way. So now, if we start to evaluate, so we plug in our upper bounds, so we get natural log of b squared. So when we evaluate this limit, what's going to happen? Yeah, so the natural log of b is going to go to infinity, minus the 1/2 natural log of 2 squared, which means we're going to go to infinity. So, since our integral ends up going to infinity, that means our series diverges. Okay, so we're diverged by the integral test. Okay there? Then, one more example here. So as we're looking at this one, let's just talk through our conditions. So positive will 1 over x cubed be positive on our domain? Yes. Will it be continuous? Yes. The only point we'd be concerned with is 0, but that's not part of what we're looking at, so we're okay there. And then as far as decreasing, if we check the derivative, our derivative of 1 over x to the third would be
Negative 1 over x.
Negative 3 over x to the fourth.
negative 3 over x to the fourth. Okay? So negative 3 over x to the fourth. So x to the fourth would always be a positive. We'd always have a negative 3 as part of that. So that's always going to be 0 or less than 0 as we progress. Okay? So our 3 conditions would be met, which means we can proceed to integrate. So I'm going to go straight into limit form here. So if we integrate 1 over x cubed, we would get negative 1/2 x to the negative 2. So then if we evaluate from 1 to b, So the part we're concerned with would be this -1/2 b to the -2. So as b goes to infinity, what's going to happen to my b to the -2? It's going to go to 0. So we would converge to, or sorry, the integral would go to 1/2, which means our series converges by the integral test. Okay?
So where would you go to trying to solve where it converges to from here? Could you do the limit of the actual a and then?
You could try, but depending on certain series, we might not ever really know what it converges to. Now, I mean, there's formulas for everything. I mean, you can find the sum of anything that does converge. However, certain series are way more difficult to evaluate than others. So while we know or while we can prove that they do converge, we might not really know what they actually converge to. So on a lot of cases, the only ones we'll probably ask you to give what they converge to are ones where we have a very simple formula to calculate that actual sum.
Like geometry?
So like geometric, we have an easy formula for. The nth partial sum problems, whatever they converge to happens to be the sum of the series. So things like that you would be expected to. But if you had to use integral test, we wouldn't necessarily expect you to calculate what it converges to, only that it does converge. Okay? All right, now, keep this example in mind. Okay, so this 1 over n cubed, we said converged by the integral test. What we're going to talk about next is what's known as a p-series. So a p-series is any series of the form sigma from n equals 1 to infinity of 1 over n raised to the p. So it could be a 1 over n, it could be a series 1 over n squared, 1 over n cubed, it could be 1 over n to the 1/2, 1 over n to the 21/5. So it's 1 over n raised to some exponent. Now the only other thing that has to happen here is that p must be positive. So p is some positive constant.
If it was negative, then would it just be like n and b?
Yeah, and so if you had like a 1 over n to some negative, then basically you're going to end up either converging or you have to work with like a n to the 1/2, seeing like what happens, but most of the time it's going to diverge. Yeah. So p would be a positive constant. Now, within this family of series, so this p series is a whole bunch of different series defined by this value or by this form. Now a special form, which is when p is equal to 1, so when we get the series 1 over n, we call that the harmonic series. And this harmonic series, I'd have to look it up again, but I think it has a lot of properties and some uses in quite a few areas of study. It shows up a lot naturally within certain things. So that's something that you could kind of investigate at some point, but it's a very special series that actually gets its own name because of its importance. So, whenever you have a p-series, in order to determine whether it converges or diverges, you simply need to look at the value of p. So given any p-series, if p is equal to 1, so if you're looking at the harmonic series, that series will always diverge. If p is less than 1, so like 1 over n to the 1/2, or 1 over n to the 2/3, or something like that, then our series will diverge. And if p is anything larger than 1, it will always converge. So, if you get a series and you're able to reduce it down into a p-series of some form, all you have to do is look at your exponent and make your determination. So if p is less than or equal to 1, it's going to be a divergent p-series. If p is greater than 1, it's going to be a convergent p-series. Now the note at the bottom here says if a p-series is convergent, we can't actually find its sum. Now there's a way to do it, but the formulas used to find those are extremely difficult, and so we don't usually mess around with actually finding what they converge to. Okay. So I think, like, for instance, the series from of 1 over n squared, I think is the one, it converges to like pi squared over 6. So as far as finding convergence values, we're not going to mess with those for p-series. So this is going to be a converges by the p-series test or diverges.
What is the harmonic series convergence?
The harmonic series does not converge. So that one will always diverge. Okay. Now, that one's an interesting one because 1 over n, the sequence, will converge, but the series diverges. So if you look at the sequence itself, so if you took away the pluses, 1 over n would converge to 0. But as soon as you start adding the numbers together, it actually never does converge to anything.
But once you get so small, it's just
It doesn't get small enough fast enough to ever actually reach. So basically what we're looking at with this p-series idea is the rate at which n grows. If it doesn't grow fast enough, it doesn't actually converge. We never actually get to a spot small enough for us to consider that no longer growing, essentially. So that's why when p is greater than 1, that denominator is growing fast enough that we can get to 0 in such a manner that we say we converge. But if it doesn't grow fast enough, it's going to continue to add more and more to our product no matter what, or our sum no matter what.
Like 1 over 100 is pretty much the same size as 1 over 101. Is that why? So it's kind of
Yeah.
Cool. Is there a particular growth rate that they consider the cutoff?
Yep, 1. So as soon as p hits 1, it's still divergent, but the minute you go past 1, so 1.00001 would be a convergent series.
completely random, but does integer and integral have any reason why they're doing the same thing? I was just thinking about that one.
Not that I know of.
Okay.
Okay. All right, so thinking about this then, that last example we did for the integral test. So we ran it through the integral test, 1 over n cubed. Now if we had known this test, all we would have had to do is
Convergence.
say p is greater than 1, it converges. So what you'll notice is in some instances, when you're looking at whether your series converges or diverges, you might choose a test, and you'll get to the point where you get convergence or divergence, but there might have been another test that was much easier to use or much easier to use. So that's one of the things too, as we continue to introduce more tests and we start looking at more and more examples in the homework, you start seeing more and more different ways to represent some of these series, you'll start to kind of pick up, I see this pattern, I know it's this, so I'm going to use this test to find it, and so on. But it also illustrates that there is more than one way to get to your result. Okay? So a couple quick examples here. If we have a series from n equals 1 to infinity of 1 over n squared, it would be convergent by the p-series test. So what you would need to say here as far as your answer, since p, well, you'd say it's a p-series, so let's start with that. So identify it as a p-series, and then say p is greater than 1, which means it converges. So however you want to do that, whatever notation you want to use, you want to identify it as a p-series, compare p to 1, and then converges or diverges. Okay? So this one would converge. by the p-series test. Now, sometimes they might disguise a p-series using some different combinations and things like that. So if we see this series, square root of n over n, yeah, what we might notice is that instead of square root of n, we could write this as n to the 1/2. And then by our rules of exponents, if I divide by the same base, I do what to the exponents? Subtract. So I'd have n to the negative 1/2, which would actually be 1 over n to the 1/2. And so now we reduce, and on a problem like this, you would need to show how it reduces to a p-series. So you wouldn't be able to just look at it and say p-series because it's not in the form 1 over n to some constant exponent. So you have to show what it comes down to as the p-series. Now it's a p-series with p less than or equal to 1, which means it's going to diverge.
What about if there's like a constant, like if it's 3 over n to the 1/2?
I think the same rules apply. We use the 1 over, but as n's going to infinity, whatever number happened to be on top to begin with becomes negligible. So as long as it's not another function of some kind, so as long as there's not another type of n up top, if it's just a constant, it's going to be a p-series regardless.
So the same would be a 3 on the bottom too, like if it was 1/3 and a 1.
Yes, I believe so.
Okay.
And that's it. Every other odd, yep.
Oops. Hold on, I'll get back to that in a second.